To introduce section 12.2, we're going to look at this example with income versus mortality rate from data from the Gapminder website. So here we have a situation where we have the income per person in a country, and this has been weighted, adjusted for purchasing power, and the under 5 mortality rate, which means per 1,000 live births, which means the number, average number of children who die before the age of 5 out of every 1,000 that are born. And we're going to look at a graph relating those two variables. So if we open up calculator here, we can see this is what the graph looks like. As income increases, the mortality rate decreases, which makes a lot of sense. But this data is not linear. So all the methods that we've done using linear regression, the linear regression t-interval, the linear regression t-test, correlation, all of the things that relate to linear regression cannot be used with this example. So rather than coming up with a whole nother model, we have a really good model with lots of statistical techniques associated with it, the linear model. It makes more sense to linearize the data, to straighten out the data using a transformation of some type than to come up with a completely new model. So that's what we're going to learn how to do. Oops, wrong window here. So we're going to look at a way to straighten out the data, several ways. We're going to start with one method. Many of the curved associations we see fall into the category of a power function. Now, a power function is just a constant times x raised to a power. And we can have kind of three different categories of this. If the power, which is b, the exponent, is greater than 1, we have something that curves upward like this. For example, y equals x squared would fall into that category. If the power is between 0 and 1, we have a graph that falls into, kind of curves a concave down sort of curve. Both of these go through the origin, 0, 0. This would be, for example, y equals the square root of x, which it could also be written as x to the 1/2 power. So this is a fractional power that curves down, but still, if x were 0, y was 0, so it would still go through 0, 0. The third one would be an inverse variation type of a function, whereas x increases, y decreases, which is similar to what we saw with the income and mortality rate example. This would be like the equation y equals 1 over x, or y equals x to the negative 1. This has a negative exponent. This one would have asymptotes. In other words, it would not be realistic in this situation to have either x be equal to 0 or y be equal to 0 in something that was modeled by this type of a curve. Now, there are ways to undo a very specific type of curve. For example, if we had y equals x squared, a way to linearize that would just be to make y smaller in relation to x. So instead of having x related to y, we could have x related to the square root of y. That would specifically undo a y equals x squared type of a curve. Here we could do the opposite. We want to make y bigger in relationship to x in order to straighten out this curve, so you could relate x to y squared. And those are two typical transformations that you see a lot, using a root or a power to transform data. However, in the interest of time, and also equally effective, is a method that will straighten out any power function. And it's using logarithms. So starting with our basic equation of a power function, if we were to take the log of both sides of this power function and just apply a couple of log rules, and I'm going to write this as a times x to the b for the purposes of what I'm about to do, we can remember that the log of a product is the sum of two logs. In other words, I can write this as log of y equals log of a plus log of x to the b. Let's split this apart. That's what one log property allows me to do. A second log property allows me to, bring the exponent out of the log, out in front like that. Little gap there. So I can write this as log of y equals log of a plus b times log of x. So now what we have is something that is in linear form, okay? Rather than this just being x and y, we have log of y is linearly related to log of x. So if we think of y equals m, or y equals a plus bx, if we write it in the terms that we usually see it in statistics, the a is the y-intercept, the b is the slope. Instead of x and y, we have log x and log y. So we have a linear relationship between log x and log y. So power functions can be rewritten as a linear relationship between log x and log y. And this could be a natural log or a log base 10. It could be any log, but those would be the two that would be used most often. So instead of writing x and y, I'm going to transform it to log of x and log of y and form a linear pattern, or natural log of x or natural log of y. Now you still might, I don't know why I dotted the natural log, that doesn't make any sense. You still might see a transformation involving a square root or square occasionally, but this one is going to always work for any power function, and it's a lot more effective than trying lots of different, more specific transformations. So if we go back and look at the data that we had on the calculator here, so here I had this mortality rate and income. And if I go, and I'm just going to show you that I've already done this on the calculator. What I did is I made two more lists. I called this one log of income, and I called this log of mortality. And on this square right here, I typed equal, and when I type in equal, this part pops up automatically. And then I did log base 10 of income. And I can get this variable income from my list. Let's see. So just kind of, let me just clear this out and just show how I did this on this one. I can say equals log. So if I do control x or control 10 to the x, there's my log base 10 of, and then I can pull down use my variable button, which would give me, it's not letting me pull that down, which is very odd. Log base 10 of variable, there we go, mortality. Okay, so then that gave me all of this data here. So notice sometimes it comes out as log and an exact value, and sometimes it comes out as decimal. It just depends whether the number over here has a decimal point in it already or not. It's the same number, so it really doesn't matter. Now if I make a graph now of log of income versus log of mortality rate instead of just income and mortality rate, then we'll see that it straighten out the data. So here's log of income, log of mortality rate. Okay, notice now my very strong, what looked like a power function here, now has become very linear. Now does it make sense that the original graph did look like a power function? I'm going to go back and look at the original graph. It actually really does, because I would not expect to have a 0 income, nor would I expect to have a 0 mortality rate. I would just expect my mortality rate to get closer and closer to 0 as the income goes up, and I would expect, I could see an income getting really close to 0, but it would be unrealistic to have either to be exactly equal to 0. So looking at this, let's go ahead and do a regression on this. So I'm going to go to Analyze and Regression and show linear regression. So we see that it looks like a nice fit with the line. I'm going to check my residual plot. So Analyze residuals and show residual plot. You can see the residual plot is very scattered. There's no distinct bend in it. We can see a fairly equal spread of the residuals across the x values. So it seems to satisfy all of the conditions for regression. So I'm going to go back to my page here that had my original problem on it. I'm going to close this here because now I have some things that I already have up here to show you. So here's the original data. Here's the re-expressed data using log of income and log of mortality. Here's what I just did. Now I also did then a linear regression, just to remind you of that, if I insert a calculator page here, I just go to Menu, Statistics, Stat Calculations, and go to number 4, Linear Regression, put in my log of income, my log of mortality, and OK, and there's what I have. Now the original picture that I have on the notes says log mort because I used a different set of data. I changed the name so that it would print again, but it's the same numbers. So here's my regression equation, slope and y-intercept, and so forth. Now how do we write this? Because this is not the original data, it's been changed. So how does that affect the way we write the equation? So notice here, when we see our y-intercept, which is the a value, and the slope, which is the b, there's my y-intercept, there's my slope, but this is no longer just x and y, or just mortality rate and income. It is log of mortality rate equals 5.04281 minus 0.989104 times log of income. So one of the things up here, it says predict the child mortality rate for the United States who has an income per person of $41,256. So I'm going to put my income in here for the USA, and when I calculate all of this, I get 0.477613. So I put those numbers in. Now how do I get back then to my original data? Well, log base 10 of mortality is equal to 0.477613. So mortality is equal to 10 to the 0.477613 power. Remember that a log equals an exponent. You take this base 10, put this exponent on it, and that's going to equal the mortality, which turns out to be 3.0034, which looks it fits definitely with what we have here. If we look at our the next closest, Sweden, has a mortality rate of 4.4. We have Switzerland, Sweden, 2.8. So with a large income, that a 3.3 mortality rate seems very reasonable as predicted here. So the predicted mortality rate for U.S. children under 5 is about 3 per 1,000. In the next video, then, we're going to look at another example that uses a slightly different transformation.